Hello everyone, my name is Minzhou Fan, and today I'm glad to give a brief introduction of our work path-guided particle-based sampling on behalf of all the co-authors. So let's describe some background and motivation for proposing this method. The sampling method is one of the big track in the Bayesian inference and typically aim to sample from a unnormalized target distribution p hat. Usually this p hat is non-normalized because it is obtained using Bayes' rule, which involves product of the prior distribution and the likelihood function, making it non-normalized. And the normalized constant is usually considered to be the intractable. Recently, people have developed particle-based sampling methods. In these methods, a vector field phi is constructed, which maps from a d-dimensional space to d-dimensional space, such that the following process here would drive the distribution of the particle towards the target distribution. Here, phi t represents the velocity of the particle. Similar to particle-based sampling, Langevin dynamics uh, can also drive particle towards the target distribution. Its stochastic dynamic can be defined as follows, with the target distribution as p hat t and bt represents the Brownian motion. It can be discretized into the following form with the delta t step. But currently, most of the particle-based sampling and sampling methods and Langevin dynamics can both be viewed as a realization of the same K or Wasserstein gradient flow. And now let's discuss some drawbacks. We take Langevin dynamics as example. Here, the target distribution is a mixture of two equally weighted Gaussians. If you perform Langevin dynamics for only 100 iterations, you can quickly discover the first mode and converge to it. However, even with 40 times more computational resources, only a few particles escaped from the mode and discovered the second mode. And this issue may be due to the nature of KL Wasserstein gradient flow. In this work, we mainly focus on addressing this drawback of the KL Wasserstein gradient flow by combining the annealing-based method with the particle-based sampling method. Our method would benefit from the relatively smooth transition between the intermediate distribution and better guide the sample as they evolve and ultimately reach the target distribution. And now I'm going to briefly describe our method, path-guided particle-based sampling, or PGPS. In PGPS, we have a predefined partition-free density path p hat t, so that we can avoid estimating the normalizing constant. And here we write this normalized pt simply for illustrative purpose. We set this p hat 0 equal to p0, which is the initial distribution, and this p hat 1 to be the unnormalized target distribution. As a particle-based sampling method, in PGPS, we aim to construct a vector field phi t. Here we use phi t theta because we want to use a parametric model to estimate it. And this ODE will drive the particles from t equal to 0 to t equal to 1. The time evolution of the aforementioned ODE can be defined, known as the continuity function. But the challenge is that we cannot directly utilize this equation because it involves a normalized PT. And in this work, we proposed a loss function to estimate the solution of the PT. And the goal is essentially finding the PT to guide the sample follow the normalized density path PT. So to better illustrate our framework, we prove this schematic graph. With a predefined normalized path at each time t, we would maintain a vector field phi to guide the sample and update the particle with this discretization. We expect this phi would guide the sample follow the path so that the updated xt plus delta t would have the distribution of the pt plus delta t. And we will continuously do this from t equal to 0 until t equal to 1. And at this point, x1 would essentially be the sample from the target p1. We found out that minimizing this infinite sample loss can find an approximation to the solution of this continuity function. And so our algorithm can be summarized into here. We would sample the initial distribution, get this initial sample dataset, and learn this phi t by minimizing the estimation of the infinite sample loss. After getting the parameters, we would update the particles by delta t. And we will continuously do this until t reaches 1, and then we would have x1 samples. Here we have the theoretical analysis for our proposed PGPS method. First, we define the delta as the approximation error. The Wasserstein error of our algorithm is essentially bounded by this. The W2, the Wasserstein 2 distance, has two terms. The first term is related to the approximation error, and the second term is related to the discretization step. You can observe that there is a positive relationship between the W2 distance and the error and the step. So the positive relationship shows that a better approximation or a denser discretization can improve the performance measured by the Wasserstein distance. And to better show the performance of our PGPS, we use this previously mentioned example here. You can see that PGPS achieves much better performance in about 650 iterations, while Langevin dynamics performed much worse in 4,000 iterations. And we further demonstrated the inference performance for a Bayesian neural network on the UCI datasets. It can be observed that in most of the datasets, our PGPS method achieves better performance in both accuracy and the calibration error, demonstrating the uncertainty quantification quality. Thanks for listening. And if you are interested in this paper or have any other questions, feel free to pop in the poster session and we can discuss about this work.